Well, we can even extend the disk and washer method a little bit. So instead of dealing with just solids of revolution, we can look at shapes that we know of, formulas for anything like a square or a rectangle or a triangle or a semicircle or a trapezoid and so on. Basically, if we're dealing with taking an area that happens to be perpendicular to the x-axis, we can take the area of formula for whatever shape we're dealing with, put it here, bounds how far left and right the shaded region goes for the x's, and integrate it with respect to x. If it's perpendicular to the y-axis, pretty much we're doing the same thing, except we're dealing with y's, our area function with y's in it, and our bounds would be how far up and down it goes. So here's a situation where we have our x-axis here, and we're perpendicular to the x-axis, coming straight out from it at a right angle, or going straight up at a right angle, and this would be a square right here. And if you do squares along the whole way, you end up getting this shape right here. If it was perpendicular to the x-axis, you get a similar shape, but slightly different. I mean, the y-axis, it would be like this here. So let's go ahead and take a look at this. We're going to have our circle. We're going to have our circle right here, which you should know is centered at the origin, with a radius of being the square root of this, so a radius of 2, which we have graphed down here. And we're going perpendicular to, in this case, the x-axis. So we go from here up, we go from here down. So this would be one edge of our shape. Now for part A, we're doing squares. So we'd have this length now coming straight out at you for that same length, and then going back to itself. Over here, if we do it here, we'd have this being the edge of a circle, so it's going to come, or edge of a square, and then so it would come out that same distance, so it's going to come out a lot farther, where when we're looking right over here, it's a much shorter distance up and down, so its square is going to be much smaller, so we're only going to come out this height. Well, if you do that, we get this shape here. And I also have physical models of this in my class that you'll be able to see in person. Now, if we're dealing with x, we need to go ahead and solve this for y. Well, if I solve that for y, I'll get a y squared is equal to a 4 minus an x squared. And I'll get y is equal to plus or minus the square root of 4 minus x squared. So in other words, this part right here would be the positive root because we're going up. This part right here would be the negative root because we're going down. And then if we're looking for the total distance, you could say, well, if I'm going square root of that up and the square root of that down, that would just be 2 of these roots for your total distance. Another way you could look at it is you could go the top one minus the bottom one. Well, when you subtract a negative, you know that you're going to end up adding, and so then we end up getting the total distance for the edge of our square to be this. So if that's the case, when we're doing our integration with respect to x, we know our bound to go from here to here, which is from -2 to 2. We know finding the area of a square is just your one edge all squared. We just figured out one edge right here, so we take that and plug it in. This right here is what we have to put in here. Now, if we go ahead and get rid of the parentheses and square both parts, we'd square the 2, we get that, we square our root, and then it cancels it out. All we'd have to do is just integrate this. Now, if you wanted, you could pull your 4 in front, and then you could just have something relatively easy to integrate. You integrate this, you integrate your 4, you get a 4x, you integrate your x squared, you get a 1/3 x cubed. Then you have to evaluate it from 2 to -2. Well, when you plug in 2 minus what you get when you plug in 4, you would get 128/3. And that would be if you're dealing with a square. Now, the second part says, instead of dealing with squares, we're going to do equilateral triangles. So in other words, this right here would be the base of an equilateral triangle, and then each side would be the same length. And so if you do that, we would end up getting this shape over here. Notice as you go towards the center, because it's a much longer distance, your equilateral triangle gets a lot taller and wider. Well, we know for the area of a triangle, it's 1/2 base times height. Or if you wanted, you could Google it, or if you maybe already know it, area of an equilateral triangle is square root of 3/4 times your side squared. Well, for our problem, we know our side is still this. So we go square root of 3/4 times your side squared. Then we could go ahead, because it's multiplication, apply your squared to each one. Square your 2, square your root, and it cancels out the root, leaving us with just this. So in this case, this 4 cancels out that 4, so we get root 3. That would be our area of our equilateral triangle. So because we are timesing by root 3, we could go ahead and put that root 3 in front of our integral sign. Then this part right here is what will go after our integral sign, because we're dealing with our x. Then once again, your bounds have to be how far you're going left and right for your x's. Well, we're starting at -2, going over to 2, because that's our circle. So now you're going to leave that root in front. You can do your integrating 4, integrating your x squared, and then evaluate it from 2 to -2. So plug in 2, subtract what you get when you plug in -2, and we end up getting 32 root 3/3.